Hello everyone, welcome to eSpace. This is the last lecture on sequential circuit analysis and synthesis, part 7. In this lecture, we will be discussing about how to design a edge-triggered flip-flop. Okay, so the edge-triggered flip-flop is a part of a clock signal circuit, as you know. But the design for the edge-triggered flip-flop is a asynchronous sequential circuit problem. Okay, so these are the steps followed for the design of the edge-triggered flip-flop: primitive float table, merging of float table, state assignment and transition table, and then finally the logic diagram or the digital circuit for the flip-flop. Okay, so this is an introduction for the design example. So we are now in a position to do a complete design of a asynchronous sequence circuit. That is, here it is the edge triggered flip-flop. So let us do that of an edge triggered flip-flop. Although this circuit is used in clock signal circuit, the design is a asynchronous problem. As I already told you, this is a thing. And these are the steps to design, as we already discussed before. State the design specification and make a state table. Derive a primitive float table. Reduce the float table by merging the rows. Then make a race-free binary state assignment. Obtain the transition table and output map, and then obtain the logic diagram using SR latches. Okay. So this is the design specifications. So to design a, we are going to design a negative edge triggered T flip flop. So as you know, the circuit has two inputs, toggle and one toggle and one clock, and then one output Q. And again you may be knowing this. The output state is complemented if T is equal to 1 and the clock changes from 1 to 0. And when the clock changes 1 to 0, then when T is equal to 1, then the output state will be complemented. Okay, and this is called negative edge triggering. That is, the clock changes from 1 to 0 is called the negative edge triggering. And then otherwise under any input condition, the output Q remains unchanged. Okay, so when clock C changes from 1 to 0, and when it is T is equal to 0, the output remains changed. On all other conditions, the output remain unchanged. Okay, and this is a flip-flop block. This is a T input and this is a clock. See, and here she is showing the negative edge. Negative, it is because it is active low, that or negative, it is shown by a bubble, and this triangle means that it is edge triggered. Okay, and this is a clock. So this is a clock signal, and this is the output signal Q. So this is a state table. So we will be listing out. There are 8 states. So first, when you see T and C is equal to 1. Okay, so when T and C is equal to 1, then initial output equal to 0, then it remains in the same state. Okay, because it is not changing. So after state A, then when clock edge goes from 1 to 0 and T is equal to 1, then it complements. So it is 1 here. Then when T is equal to 1 and C is equal to 1, and when initial output is equal to 1, it remains in the same state, that is in the 1. Then this, when 1 0, you can see from the state here, when then 1 to 0 and T is equal to 1, it complements, that is after state C. And then after D or state F, this when it goes to 0 to 0, so and it remains in the same state 0, and F it after E or A, and when it goes from 1 to 1, and when T is equal to 0, so it remains in the same state, that is state A, that same state 0. And when then this is what when B or H, when it goes from 1 to 0 and T is equal to 0, it remains in the same state 1. And then it is after G or C, you can see here, when it is going from 1 to 1, C is going to 1 to 1 and T is equal to 1 to 0, so it is the same state 1. So that is after G or C. Okay, I think you understood. And let us now derive the primitive float table from the state table we have got from the design specifications. Okay, so first we'll see state A. State A means it is T and C is equal to 1 1 1. So yeah, this is the state 1. So as we have already told before, in the fundamental mode, there should be only change in one variable. Okay, if there are change in two variables, then it is a it is an unallowed state. And some here it is 1 1 means it remains in the same state, that is it is A, and it is in 0. So this is, we have got the first state A, the stable state A. This we had done before in the design of a gated latch. You may be remembering. Okay. So this is A to A. This is in the stable state 1 1. You can see 1 1 0. And this is the unallowed state where there are two change in two input variable. So it is 0 0. So that is given by dash dash. Okay. And then now let's see 1 1. This is state A. 1 1 0. When it goes to 0 1, you can see here 1 to 1. C is going from 1 to 1 and T is going from 1 to 0. So 1 to 1, it remains in the same state 0, though it is, you can see which is 0 1 0. So it is F dash, and then again A goes to 1 0. So C is changing from 1 to 0. So there will be change in that Q output, and it is T is equal to 1. So it is complemented. So 1 0 1. You can see where is 1 0 1. It is B. So it is B dash. Again go from B 1 0 1 0, and it is B1. Okay. And unallowed state is unallowed transition is 0 1. You cannot change from 1 0 to 0 1. So you can I put dash here. So let us now see this B, that is 1 0 output 1. When it changes to 0 0, C is going from 0, so there is no triggering. So the output will be in the same state, that is 1. So it is 0 0 1. It is G. Okay. And again 1 0 1, and then it is going to 1 1. So it is positive edge. So there will be no change in Q. So which is 1 1 1. It is C. Okay. Okay. So I'm going to erase this. So we have got now A and B. Now let us see C here. C is 1 1 1. So again this is the state 1 1. There will be stable state C1. Okay. And then 0 0, which is unallowed state. So that will be written by dash dash. Let us see here. C is 1 1 1. Okay. And when it changes to 0 1, okay, then C is in the same. So there will be no change. So it is 0 1 1. See here 0 1 1 is H. Okay. And again we'll put 1 1 1, and it is going to 1 0. So C is changing from 1 to 0. So there will be a change in that. The output will, there's an effect in output. So, and because T is equal to 1, it will be complemented. Okay. So it is going from 1 0. So we have to set 1 0 0. That is D. Okay. So you got D here. So D 1 0 is a stable state. D and 0. So, and the other unallowed state is 0 1. So this is for that 2 dash. Okay. So D is 1 0 0, and you can see when it changes from 1 0 to 0 0. Okay. See, there is no change in clock, so no change in data output. So 0 0 0. So it is E. Okay. And 1 0 again 1 0 0 to 1 1. There's a change in 0 1 0 to 1. We have taken negative edge, so it is, there will be no effect. It will be 0. And 1 1 0, it is A. Okay. Now let us see E. E is 0 0, so the stable state E and unallowed state. Okay, and it is E is 0 0 0. So when it changes to 0 0 1, there's positive, so it is again the same state. 0 1 0, you can see here it is 0 1 0 1 0, it is F. Okay, so again 0 0 0 0. Okay, and it changes to 1 0, again the same state 0. So it is 1 0 0, it is D. Now let us see F, it is 0 1, so it is F 0, F output 0, and 1 0 is unallowed state, so it is rounded to dash. So F, you can see here 0 1 0. So when it goes to 0 0, T is 0, it is in the same state 0. That's a change, it is negative edge. So because T is equal to 0, it is in the same state. It is E, so it is E here 0 0 0 E. So you can see here again 0 1 0 1 1, same state to 0 1 1 0. It is A. So now let us take G. Okay, is defined by 0 0 1. Okay, G, this is the stable state is 0 0 and unallowed state is 1 1, so the dash. Now let us see the other two conditions. 0 to 0, when it changes to 0 to 0 1, 0 0 to 0 1, so that's a positive edge. There's no change in data. This one 0 1 1, there you can see it is H. Okay, again 0 0 1 changes to 1 0. The T is changed, but C is not changing, so the data will be in the same. So that is 1 0 1. You can see here where is 1 0 1, this is B. Okay, so now let us see the final state. H, the stable state is 0 1, okay, so H1, and then the unallowed state is 1 0, it is a 2 dash. Okay, so H is defined by 0 1 1, when it changes to 0, here the clock is changing from 1 to 0 and T is equal to 0, it is in the same state, so it is 0 0 1, where 0 0 1 it is G. Okay, then again 0 1 1 2 1 1, so it is the clock is not changing, so it is same data, same Q. Okay, output will be same. Okay, so it is 1 1 1, where you can see 1 1, so it is C. Okay, so now we have finished filling the primitive float table. Okay, now let us go to the next step. Okay, so this is state table I done. Okay, according to the float table, I had defined the state table. Okay, you can just go through, you can make it like this. I'm not going into details. Okay, so there are more number of states, so we'll be using a implication table to reduce the number of states as done before in the previous lecture. Okay, so let us see here. First state is first pair is A and B. See here, A and B. See, it is not equivalent. There's a difference in A and C. So we'll be putting a cross mark across it. So AC cross. Okay. Then AC. See here, it is again not equivalent. Okay. So the cross. Then AD. See here, AD. It's again here BD. That's a cross mark. Okay. Again AE. Same like that. Okay. Then AF. That is AF is equivalent, so it is put a tick mark across it. Okay, then AG. Okay, AG. AG, you can see it is not equivalent. Okay, FH and AC. Because of FH and AC, it is not equivalent. Okay, and let us see BC. BC again BD is not equivalent. Okay. Then BD you can see it is not equivalent. Okay. Then BE you can see again not equivalent. Okay. BF see here AC is a EG and AC it is not equivalent. Okay. Then BG it is equivalent. See you can see here BG same states. Okay, same next state and same output. Okay. Then BH again that is also equivalent. Okay, you can see here BH same states and same output. Okay. Then C this one CD. Okay, CD can see it is not equivalent. AC because of AC it is not equivalent. And CE C not equivalent because of CE because of FH. Okay. Then again CF is not equivalent. Okay, you can see here CG can see here B and D because B and D it is not equivalent. Then CH it is equivalent. Okay. Then DE it is equivalent. Okay. Then DF again it is also equivalent. Okay. Then DG not equivalent because of EG and BD. Okay. And DH see here DG is not equivalent because of DE and CF. Then EF it is equivalent. Okay, same next state and output also same. Then EG you can see here it's not equivalent because of F and H. Okay. Then EH not equivalent. Okay. Then FG you can see it is not equivalent because of EG and FH. Okay. Then FH you can see it's not equivalent again. Then you can see GH. Okay, see here it is same, so that is equivalent. Okay, so now with this technique we have to make pair, so that is AF BG BH CH and DE DF and EF and GH. Okay, so these are the equivalent states AF BG BH CH D DF EF and GH. Okay, now let us do with the merger diagram. So again I listed here the all the pairs of equivalent states. Okay, so these are 8 states done in the circumference of a circle. Okay, and then we have to draw a line between which are the equivalent pair. Okay, so first you AF. Okay, AF. Okay, so you got the line here, and finally we'll make which are the maximum number of sides of a polygon that will be the reduced state. Okay, which is AF, then BG BH CH DE DF EF and GH. So here this can be grouped here, BGH can be grouped, and then DEF can be grouped, and this BGH can be grouped, and DF can be grouped, and AF and CH. Okay, so these are the maximum compatibles obtained from the merger diagram are okay AF BGH CH and DEF. Okay, and just here AF you can see AF, this cannot be reduced more. Okay, and BGH, this is a BGH, this triangle. Okay, then CH and CH, this is one pair. Okay, that is only one line, we cannot reduce it more. Okay, CH and DEF. Okay, this is the pair, so we got this can be reduced to one triangle. Okay, so let us see the reduced float table. Just saying written reduced it to 4 state from our primitive float table. Okay, you can also make it. I'm not going into details. It's very simple. Can just work it out. Okay, and this is this we are combined A and F. We are made into A, BGH to B, CH to C, and EF to D. Okay. So here you can see here all I have written A, B, C and D. Okay. Now there are only 4 variables for states, that is A, B, C and D. Okay. Now let us see the state assignment. Okay. We have got A, B, C, D. Okay. Now I'll according to this I'll make the transition diagram. Okay. Now let's see here A to A to B and A to D is there. Okay. Then B to B, B to C and B to C is there, and C to B. Okay. And C to D. Okay. And then D to A. Okay. So let us say the state assignment. Okay. A to B, B to C and C to B. Okay. There are both directions is there, and C to D. Okay. And A to D and D to A. Okay. Now let us see here. There are no races by seeing the diagram. Okay, because all transitions are happening with only one input variable. Okay, one input variable change here. All are one input variable change. Okay, so there is no race, and we can make this state assignment as the most reduced one. Okay, most reduced state assignment. Okay, according to the transition diagram. Okay, if there are diagonals only, there will be a race. Okay, here there are no race, so it is this one itself is the race free state assignment. Okay, so this is a transition table I have written. Okay, just transition table, as you know, it is the same thing as the float table, just replace with the variables for the states given by letters. Okay, this is the output map. Okay, you can see here some don't care states, that is a don't care that is the unstable states, that some we have to make it 1 or 0 to make a stable transition. Okay, so this is the reduced flow table I have regenerated here. Okay, so let us see this don't care. See here, it is when it is in state A, when 0 comes, it goes to state D. Okay, so here you can see it is D here, it is comma 0, so this should be 0. Okay, and here this don't care, this it is here X. So here you let us see here it is A, when it is 1 0 it goes to B and it goes to D, but as it is going to two output values 0 or 1, this should be don't care, it should be X. Okay, and this one, now this one you can see B to C, and C it is C it is going to 1, so stable state 1, C it is 1. Okay, so here it is 1. Okay, again here C to B, it is B it is not changing, the output is 1, so this should be 1. Okay, and here again D, can see here D is again that should be don't care, this it can be 0 or 1, so it is here, it is don't care. Okay, and now we can see here this one A is 0, so it is, you should put here 0. Okay, so we assign those values. So here can see, so we can group this one, and so it is Q is equal to Y2. Okay, that is the result. Okay, so now we have to implement this the circuit with SR latches. Okay, so we will find the values which has to be put in the K map according to the excitation table shown below for SR NAND latch. Okay, this is the excitation table for SR NAND latch. Okay, now we have got the K map for that. Okay, from the where, from the transition table. Okay, so now let us group here. Okay, okay, so there is, you can see here when it is 0 to 1 transition. Okay, it is 1 0 like that. Here we have to make all the values in the K map. Okay, and now we have got the value S1 equal to Y2 TC plus Y2 bar TC T bar C bar. Okay, and then R1 equal to Y2 T bar C bar plus Y2 bar TC. Okay, this we have repeated the same procedure for the as we have done in the gated latch. Okay, you have got S1 R1 and this S2 R2. Okay, and from these equations we have to make the logic diagram. So this is the logic diagram. Okay, You can see this is the edge triggered T flip flop. Okay, it is not a master slave or otherwise a simple gated latch. No, it is a edge triggered flip flop. Okay, made with two SR latches. Okay, according to the equation. So yes, here. Okay, so that's it, friends. This is the end of this lecture. So it is the end of the part. Okay, the sequence circuit analysis synthesis. Please like and share the video. Subscribe the channel. If you have any doubt, send mail me to chanch484@gmail.com. If you have any doubts, okay, or otherwise you can put in the comment section. Okay, thank you.